Yeah.
Okay. You guys ready? Yes, no, maybe so.
Yes.
Okay. So, first question. How are our confidence levels on this one?
0.
Oh, okay. That's not what I expected out of this one. Can I get a thumbs up, thumbs middle, thumbs down? Okay. Middles and downs. Where were you struggling? Drawing. Okay. So maybe we need some more practice with naming to drawing. The first thing we'll do is break up our name into all of the important information we can pull from it. So 2-propanol. What does prop tell us? 3 what? 3 carbons. What does AN tell us? Yes. Single bond. What does OL tell us? Alcohol. So we should have an OH group. And what does this 2 tell us? The location of the alcohol. So we need 1, 2, 3 carbons. We need an OH on the second carbon, and everything else can be filled in with hydrogens. So that's 2-propanol. Everyone following so far? Okay. We're going to do the same thing with our other one. So we have bute. What's that tell us? 4 carbons. We have another AN. What's that tell us? Single bonds. We have oic acid. What does that tell us? Carboxylic acid. What's this methyl tell us? There will be a methyl group. And our 3, where does that go? So if that's the location of the methyl group, where is our oic acid?
1.
So we can take our 4 carbons. We can make 1 into a carboxylic acid. And then if this is our 1, we need to put a methyl on the 3. And then we can go fill everything else in with hydrogens. So there we have our 2 starting materials. It's easier to do this with the skeletal structures, so I'm going to change them to the skeletal structures. So we're going to do a condensation with these 2 reactants. In order to do so, we need a catalyst of some kind, and we're going to make an ester. What does an ester look like? Okay, what makes it different from a carboxylic acid? Yes. So we are going to combine our alcohol and our carboxylic acid. Basically, we're going to cleave this here and add our alcohol. So we have this breakdown. And so we're going to make water, not ester, from our alcohol and our carboxylic acid. And this is an esterification. We can also do thioesterification or an amidification. And that is just changing our alcohol to those other functional groups. So a thioester would be a thiol instead of an alcohol. And an amidification would be an amine instead of the alcohol. But the one thing that will stay true to all of these carbonyl reactions is you need to have a carboxylic acid. How are we feeling on that one? Up, middle, down? Mostly ups from the people who are responding? Okay. Question 2. Anyone feel confident about this one? Okay, we've got one answer for delta. Anyone else? We've got a few for gamma. So, where do you start with this one? The one away from the carbon. So, how we number these is just using the Greek alphabet as a numbering system. So instead of 1, 2, 3, we have alpha, beta, gamma. So the correct answer for this one is gamma.
So we don't start the carbon after the carbon. You started the carbon first from carbon group.
Yes.
Yeah, I think started the carbon on the other way. Yeah.
Oh wait, that seems right. It doesn't change the answer, no.
But did that impact? Maybe.
I'll get back to you with a better answer on which way it is. I'll have to delete to be sure, because I don't want to lead you guys astray. Which substrate will form the following lactose? And what kind of lactone is this? Do you guys have any thoughts on how you would start this reaction? First of all, how many reactants will we have?
2. I feel like it's 2.
I feel like it's not.
I feel like 1.
I feel like it's 1. So, in making a lactone, we've basically made a cyclic ester. And so, we break the bond there, and we flatten out our molecule. What are we missing when we flatten out the molecule?
The OH.
Mhm. Where would we add the pieces of water?
The OH is different.
Like that?
Yes.
What else? Are we missing?
And then an H with the other.
Yes. So it's an intramolecular esterification, and that's how we get a lactone. Questions on this one? What kind? We'll get there. I want to make sure people feel good about the.
The difference between the two oxygens, so the oxygen and the carbon that has.
So, what kind of lactone? What are we feeling? Oh, it is the after the carbonyl, because it makes sense with this one. Which also kind of gives you the answer. So we have our carbonyl. Alpha. Yeah. Our alcohol is on the gamma carbon. And it closes it. Yes, no, maybe so. Thumbs up, middle down. Down. Okay. How can I help it not be down? Type is a very broad question to assume. With this, yes. I think for this exam, yes. Just think alpha, beta, gamma. What's up?
So it's gamma because there's four of like the O, we're always looking for OH.
Because the OH is on the gamma carbon. So like I could have kept going with this carbon chain. And then we would have had extra carbons off of this. Or if the alcohol was on a different carbon, like the beta carbon, it would be a tighter lactone. Period. Good on this question? Okay to move on? Yes? Okay. So, dextroamphetamine. This is a chirality question. How many possible stereomers exist? And how do we find this out?
So that's when you find how many chiral centers there are. Is it like
It's two.
Two to the power of the number of chiral centers. How many chiral centers does this molecule have?
just the one?
Just the one. Where?
Between that is the reactions.
So 2 to the power of 1 is Two. So we have two possible stereoisomers. In this question, we have already been given one of the enantiomers. What is the other enantiomer? And how would we draw it?
Did you just switch the wedge to attach?
Exactly. And there we have it, our two enantiomers. Questions on that? That's cool. Okay. Questions on this one so far, and then we'll do C. Okay, moving on. What is this question asking? An acid reaction. What is our acid?
Hydrochloric acid, HCl.
What is our base?
Extra.
Yes, what part of it though?
The
You mean? What happens in acid-base chemistry? What are we moving around? Protons. So who is going to get a proton and who is going to give a proton?
the meme's gonna get from
From who?
H.
From HCl, yeah. What is HCl once it gives out that proton? Cl minus. So how many protons does our nitrogen have now? 3. Can I, bless you. Can I just leave it like this?
You put a charge on the H.
Yes. What charge?
Positive.
Positive. So that's our balanced chemical reaction. What functional groups do we see in this product? Methyl. Aromatic ring. What's the like official term for this? And what's the last term for it? Benzene. What else? Yes. So how many, is it a primary, tertiary? What kind of amine is it?
Would that be?
Mhm. And then there's one last one that you might not have gotten. We have aryl. And aryl is basically just another name for the ring. But you guys don't have to know that one. We have plenty of terms for it. Questions on part C of this question? What's up?
Why is it quaternary?
It's quaternary because we have 3 hydrogens and 1 carbon bond, so the nitrogen has 4 bonds. Ready to move on? Okay. Classify the following reactions as a reduction, oxidation, and explain why. Thoughts on the first one? Why? What increases? Mhm. What functional group is this one? And what does it change to? What about the second one? Oxidation, reduction? Reduction. Why? What is this functional group called? Alkene. And what does it transform to? How many does the CH bond increase by? 2. What about the oxidation reactions? What are they changing by? Questions on this one? Yeah. Yes, because you had to classify it as a reduction or an oxidation. And that's like a type of those reactions, but we're looking for reduction. Oxidation. Other questions? Okay. Draw the possible products. How many products will there be? 2. What exactly are we doing in this reaction? What are we going to change? To what? We're going to add an alcohol. Where are we going to add an alcohol? No, not quite on the methyl. What's the other functional group we see here?
Get rid of the alcohol.
Yes, you'd get rid of the alkene. So we're going to get rid of this and we're going to add an alcohol. Should I add it if we number our carbons here? Or should I add it? 2? Why do you say 2?
You gotta put it where the alkene wasn't so small.
What? How many products did we say we're going to have? 2. Where do you think the second one's going to go? Yes.
How do you know you're going to have 2 products?
Because the alkene is just as likely to break to one side as the other and have the alcohol add there. If we were doing more complicated chemistry, we could talk about directing groups and electron withdrawing and donating and how that would change what the major or minor product is. But for our purposes, there are 2 sides of the alkene. It can add to either side of the alkene.
So what we found this on examples of products.
The exam has not been written yet, so I can't honestly answer that question. But I feel like the practice problems have been pretty similar to the exams. What's up?
Now, if the methyl group wasn't there, would there still be two products or would it not matter?
There would not be two products because the two products would be identical. So yeah, the methyl group is how we get two unique products from that. Yeah, what's up? Water is not usually a catalyst. It's the sulfuric acid is the catalyst. The water is a reactant. Yes. Yeah. This would technically also make H3. No, it wouldn't. Because the other hydrogen goes to the other carbon. What's up?
Why did you get without
So with the methyl group, we can see that there's one product where there is no carbon separating the methyl and the alcohol. Or there's one carbon separating the methyl and the alcohol. So those are two unique products because either they're connected in neighboring or they're connected by off one. If we got rid of the methyl, and just drew out the same products, these two are the same thing. Like if we were to name them, they're both one cyclo. Whereas if we were to name this, we would have two. Yes. Yeah. What's up?
Is this like simple hydrolysis?
I would call this a hydroxylation. Hydrolysis is usually using water to split something. Whereas this is adding a hydroxy. Yeah. So because it's catalytic, it'll be restored by the end of it. So it will help put a hydrogen on the other half of the alkene. And in giving a hydrogen there, it'll take a hydrogen from the water. And so it ends as H2SO4. So nothing changes about it. Other questions? Good to move on? Okay. Draw the possible products for the reaction below. What kind of reaction is this going to be? It's kind of a reduction, whoever said that. So what kind of products, like what functional group are we looking for in this product?
Carboxylic acid.
Where are you getting your oxygen from? Okay. Hey, you're making an attempt, but you're going the wrong direction. So that's an oxidation. If that's the wrong direction, what is this?
We're adding hydrogen. Oh, we're getting rid of.
No, not quite. That's also an oxidation.
Something with tiles.
What?
Throw the alcohol away.
Throw the alcohol away. We are definitely going to do that. So we're not going to throw just the alcohol away. We're going to make water.
So condensation. Oh, so the heat. So if there's a temperature condensation. Like, or no.
I'm not sure if that will always be a rule, because there are some other things that use heat as a catalyst. But yes, this is a condensation. Because we're gonna lose water. Yes, that can help guide you. So, if we're gonna lose water, we're gonna lose this OH. Where are we gonna get that other proton?
From a carbon.
From a carbon. What happens if we take away? So we're gonna take away the OH. We'll say we take it away as OH minus, which means we'll have a plus here. Do you want to take from the carbon on the left or the right? The right? Okay. So we'll lose an H plus, so we'll have a minus here. What are we gonna do with this now?
A double bond.
A double bond. Is this the only answer we could come up with here?
No.
No. What's the other answer we could come up with?
The other side.
The double bond on the other side. So these are our two products. Which one is favored?
The one on the left.
Left or right? Who feels strongly and wants to talk me through their thoughts?
Thanks. I feel like it's weird to have a double bond carbon on the end.
Mm-hmm. Terminal.
Okay.
It is odd. And that's because when we have the minus inside, it's better resonance. So this is going to be our favorite product. Questions on that? So when we put the minus interior, it has better resonance because you can kind of shift around more. But if you're on the end, there's nowhere to shift to. But if you're in the middle, you could shift to the left or to the right. Yes. What's up? These are both oxidized to the same degree. Rather, they're reduced to the same degree. 1 second. Yeah.
So I thought it was supposed to go, like it still works, but to the carbon that had less hydrogen attached to it.
It's the same thought process, but that's probably an easier way to remember it,
Okay.
as that one has less hydrogens. I'll write that down. What was your question? That is just showing the intermediate step of those electrons have to go somewhere. You don't have to know that kind of intermediate. It gets more into like electron pushing, but that's like the chemistry behind why it can make an alkene. If you want, I can go into more detail about it, but you don't have to know that detail. Okay. Feel good about this one? Yes, no, maybe so? Okay. Consider the compounds G and H, circle the chiral center in each compound, and then we're going to draw both enantiomers of each compound. So, let's start by numbering our carbons. I'll start with this one. Actually, we're numbering the chain. Which atom is our chiral center on this one? Why?
sp3. There's no double bonds and all four groups are separate.
Mhm. What changes do I have to make to this drawing to make it shown that it's chiral?
Which is the H. Oh, I don't, sorry. Mirroring.
Eventually, yes. But what am I mirroring right now? Because currently I have it drawn as them all being in plane. What do I have to add to give this drawing, this 2D drawing, some kind of 3D? Yes, I need wedges and dashes. Does it matter where I put them? No, because we're drawing it from a 2D image. So we don't actually know what they are, but in this case, we're just trying to make one enantiomer and then another. So I'm gonna make my nitrogen. And then I'm gonna make the hydrogen wedged or dashed. How do I draw the mirror image of this? Or the enantiomer, sorry, kind of give the answer there. Yes, exactly. I'm not picking random places. It's on the chiral center, but I can pick random substituents because we don't know what the actual answer is. So, question 8. Consider the compounds G and H. For H, we're going to start with numbering our carbons, or maybe just like our main parent chain here. And we're going to look for what carbon has 4 unique substituents. So, carbon 1 has 3 hydrogens, so that's not going to work. Carbon 2 has 2 hydrogens, so that's not going to work. Carbon 3 has 1 methyl group, 1 ethyl group, 1 hydrogen, and then kind of the rest of this chain. So carbon 3 is going to be our chiral center. So we'll draw out compound H. And then we will add our wedges and dashes to show that we have a 3D structure. So I'm going to make my methyl group wedged and my hydrogen dashed. And our enantiomer for this, we're going to draw out the same base structure. And then we are going to switch our wedges and dashes. So we'll make our methyl group wedged or dashed and our proton the wedge. So these are the enantiomers. If you caught the original recording, I misidentified this center. this center is not a chiral center because these are both methanol groups. Or a methyl hydroxy. So we don't have 4 unique substituents at that spot. So classify the bond between the carbohydrates that compose lactose. What are the 2 necessary parts of this title? We're going to break it down the center. What are the 2 parts we have here? We have alpha beta, and then we have numbering. What does the alpha beta mean? Mm-hmm. If we were looking at a monomer, what would it mean?
It would be
Sort of?
the OH or top or bottom.
Yes. OH on top or bottom. So this tells us the direction of the OH slash the linkage. What means what? Yes. Alpha equals down, beta equals up. I don't know about you guys, but when I draw a beta, I draw it upways. So it's like an arrow. And that can help remember. You can also draw your alpha signs down. So is this an alpha or a beta linkage? Beta. So we can knock out all of our alpha answers. How do we number? Do you start at the oxygen or do you start at the carbon next to the oxygen? Which carbon next to the oxygen? I don't know which one it is.
It just it's
Yes. Numeric carbon. That's going to be the carbon next to your oxygen that has an alcohol. Because see how this carbon, no alcohol. This carbon used to have an alcohol, now it's in a linkage. So that's going to be our bond. Where do we start counting on the second monomer?
the same spot.
The same spot. 1, 2, 3, 4, 5, 6. Where are we linked? 1 and 4. So the correct answer here is the beta 1,4 linkage. Questions? Comments, concerns? Yeah. So we read right to left. So that's why it's 1 to 4. It also is like lowest to highest, but it's mostly like the right to left. Yeah. The bottom one was linked at 4. It would just be a flip of this where it's still a 1,4 linkage. Because if we connected from this one and we drew out our group here. Right to left, this one would still be attached at 1, and this one would still be attached at 4. Other questions on this one? Okay. Which substrate, when oxidized, will form the following product? What part of the molecule are we interested in for this question? The carboxylic acid. So this question kind of has us working backwards. So what substrate will be oxidized? What's another way that we could word this? Mm-hmm. So, what are our options here? There's 3 answers, 2 are more right than the other one. An alcohol is definitely one of the options. The aldehyde is another of the good options. If we reduce an alcohol, what do we get? Sort of. It gets down to the methyl group. So our order of events is the carboxylic acid will go to the aldehyde, which will go to the alcohol, which can go to the methyl. These two, more correct than the methyl. It would take a lot to get it all the way down to the methyl.
So you could completely lose the other alcohols.
Mm-hmm. Questions on this one? Moving on. So the first step of question 11, we're going to do the Fisher projection of D-glucosamine. So first we can count out our carbon chain, and then we can straighten it out. So we have 1, 2, 3, 4, 5, 6 carbons. We have that double bonded oxygen on one end, the alcohol on the other, and then we can fill in our wedges and dashes. So the first step there is to straighten up or straighten out our skeletal structure. The next step, we are going to flip everything to be on the same side. So when we flip, we change what kind of wedge we're going to use. So although this one is dashed going down, when we put it up, it'll be a wedge. The next one we can keep the same. The third chiral center, we have a wedge going down, so we'll have a dash going up, and then we can keep our NH. So now we have everything on the same side. We are going to determine which is our D-glucosamine. So our D is going to be the farthest from the carbonyl. So our carbonyl is here. So this is our furthest. And that is a wedge. D means to the right. So for that, our wedges will all be to the right. We can also go ahead and fill in our end caps and our other hydrogen. So if wedges are to the right, our dashes will be to the left. And then we can fill in the rest of our Fisher projection. And so which carbon is this key stereocenter that determines whether it's D or L? It is this carbon here, which is the furthest from that carbonyl. And a carbonyl is just the double bonded oxygen. So moving to our cyclic form. The alpha tells us the direction of the hydroxy on the anomeric carbon. So our anomeric carbon, if it's alpha, it will be down. So we can put that in. And we also know that because we have a D-glucosamine, our CH2OH will be up. And that's going to be the same in both the beta cyclic form and the alpha cyclic form. And then what changes with alpha versus beta? Alpha is down, beta is up. So our OH will go up on this one. We'll have our hydrogen go down. And now we can fill in our other substituents. And so for this, if it's on the right side, it'll be below the ring. If it's on the left side, it'll be above the ring. So we have our nitrogen goes down, our OH goes up, and this OH goes down. And that'll be the same on both cyclic forms. And then we can fill in our hydrogens. So if we want to keep up with our counting from our original structure, we can go through and count here as well. So this would be 6, 5, 4, 3, 2, 1. We can then go through here, 6, 5, 4, 3, 2. And so our D glucosamine, this stereocenter, how it determines that is whether this CH2 is up or down is how this OH connects into the ring. So if it is on the right, it goes below, which means our other substituent, the CH2OH, will go up. We can number on the beta form as well. And there our carbons are all numbered the same. So that's the Fisher projection and both of our cyclic forms. Next is D-glucosamine, best described as an aldose or a ketose. When we look at this, do we have an aldehyde or a ketone? We have an aldehyde, which means this is an aldose. Remember that the aldehydes are terminal while the ketoses are in the carbon chain. Next, classify it as a pyranose or a furanose. A good mnemonic device is F for 5. A furanose ring has only 5 members in it. We have 6, so we are dealing with a pyranose here. The next part is looking at the specific stereochemical relationship between D-glucosamine and D-galactosamine. So if we compare across the two here, the only difference is on this third carbon. And on this third carbon, we have a different chirality. So the stereochemical relationships, you have stereoisomers is the umbrella term. And you can have enantiomers, or you can have diastereomers. enantiomers are where you have that mirror image. Diastereomers is basically everything else. Because we only changed the chirality of one center here, we are not dealing with an enantiomer. So this is a diastereomer. Finally, draw the products that result from a mild oxidation and a strong oxidation of glucosamine. So if we want to draw it out with our Fisher projection, our original looks a little something like this. And if we were to mildly oxidate, we could turn our alcohol into aldehydes. And so we have an alcohol right here that we could turn into an aldehyde. And that would lead us to this structure. We can oxidize one step further because both of these aldehydes can now become carboxylic acids. And our shorthand notation for that can either be CO2H or COOH. But both of these end up as carboxylic acids. Another option here is turning any of these alcohols into aldehydes, well, into ketones. So in that case, you could have something that looks like this. Moving to question 12. Fatty acids. How can we structurally notate fatty acids?
Unsaturated.
Yes.
Oh.
Like, how do we write it out?
Like the W
That's part of it, yeah.
or the 18.
Carbons to double bonds. So you have number of carbons, the number of double bonds. So for the first one, what's that looking like? Zero. What about B? What's the W way to name it? What about our next one? How many carbons? How many double bonds? What number follows our delta?
So with the delta, you on something, okay, you kind of from the carboxyl gas, right?
Yeah.
So delta 9 is 12.
What about that way? 6. What about the last one? 18.3. What's our delta? Which of these would have the highest melting point? Yeah. I heard it. A. Why?
Left double.
More carbons is a higher melting and higher boiling point. Less carbons is going to decrease that. And then if you add more double bonds, that's also going to decrease it. Questions? You need to number them left to right for one naming way and right to left for the other naming way. So for your deltas, you number starting at the carbonyl. And for the like kind of curly W's, you number from the opposite of the carbonyl. Okay. Last question. You want to do the saponification or the hydrolysis first? Saponification. Okay. What does it mean to saponify? What are we going to do? What do we need? Actually, is maybe a better question. Which is sodium hydroxide. Why are these also skinny? So, what are we going to do as we saponify? Are we going to form bonds? Are we going to break bonds? What bonds are we going to break? On what side of the carbonyl do we break it? Yeah. How many molecules are we going to make at the end of this? 3. What am I missing here? The NAs. What's the difference for a hydrolysis reaction?
Adding water.
We're gonna use water instead of NaOH. How is that gonna change our final products? Instead of Na, what do we have?
A.
So we have OH in both. Maybe this is better if I draw it like this. We have OH in both. What's the difference?
Hydrogen.
Hydrogen. So instead of having the salts, we'll be able to complete the carboxylic acid. So instead of having a carboxylate, we'll have a carboxylic acid. Questions on this one? Questions in general? Questions on the homework that's due tonight? Yeah. I have one more office hour on Friday before y'all's exam. It's my normal office hour. So if you have last minute questions, you can stop by then or ask them now. What's up? It's this one. Oh God. It's this one and this one. I just didn't draw out the entire chain.
Whenever we're taking a molecule,
Yeah.
where to begin? So like, so where do we get like two H's from? Where the two O?
So this oxygen will end up here and here. And these hydrogens will end up here and here. Yes, so we would need 2 NaOH for this and 2 water. Because we're cleaving 2 bonds.
Thank you.
Do we have to know these things?
Yeah.